Welcome everyone. Hope you're all doing well. This is the third video series where we'll be discussing section 7.3 of McGraw-Hill Ryerson on the dot product and its applications. So some preliminaries. All the applications of the dot product I listed here, and there's some important formulas we need to know. So we need to know what work is. It's the capacity. Yeah, we need to know work, the angle between vectors, and the formula for vector projection. Now, the latter of these, you should know where it comes from, its derivation. I'm going to be using it here quite frequently, just looking at the formula because I sometimes forget. But you should be able to derive it and understand it if I change maybe what I label as U or V. All right, let's get into it. So, question 1. Determine the work done by each force in newtons for an object moving along the vector s in meters. So here we'll be using the first formula on work. So I'll be choosing at random which questions I do. I'll not be doing all of them for this part of the video series. 1a, so let's do F dot S. I guess I should call it work. .74, which is just 5 times 7 plus 2 times 4. And we get 43. Okay, and C. So this is 67.8, so F dot S. I always like to write the formula down before I start the problem, so I know what I have to input. 67.8, 3.9, it's an ugly 3, 4.7, 3.2, same deal, 67.8, component-wise multiplication, and then add. Times 3.2. So the answer we get is 331.1. That's an ugly 3 again. And both these units are joules. That's the standard SI unit for work. Okay. Moving on. Let's do question 2. Determine the work done by the force in the direction of the displacement. Nothing really changes here. It's the same formula, but instead of using the Cartesian form of the dot product, this time we use the geometric form of the dot product. So I should... Yeah, so this time we're using the geometric form. Should label which questions I'm doing. Let's do B and C. $350 times 42. Cosine of 30 degrees. And then for C, same deal. Which will be 45.2 times 241. Cosine of 80 degrees. And calculate. 350 times 42 cosine of 30, 12,730.57 joules. 45.2 times 241 cosine of 80, 1,891.58 joules. Okay, so before moving on, I just want to highlight one thing. The formula that I wrote down here for work, I just wrote down F.S. I wrote it very generally as just being the dot product. This could either be the Cartesian or the algebraic dot product. I didn't really highlight which one I was using, and that was on purpose for this, for both of these exercises. Okay. You have to choose which one you use depending on the information you're given. You could use either one, realistically speaking, but one will always be more convenient to use. Like here, for example, for question 1, I was given the vectors in Cartesian form, so I chose to use the Cartesian dot product. And for the second question, I was given magnitudes of the vectors and the angle between them, so why not just use the geometric dot product, right? Perfect. Okay, question 3. So let's do C and D, I guess. Yeah, let's do CD. Again, I'm just choosing at random. So it says calculate the angle between the vectors in each pair, illustrate geometrically. Alrighty. So we have -7, 2. 1, 2, 3, 4, 5, 6, 7. -7, 2. 1, 2. And the vector 6, 11. 1, 2, 3, 4, 5, 6, 11. Yeesh. I have to redo this. Quite bigger. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So we have the vector -7, 2. 1, 2, 3, 4, 5, 6, 7. -7, 2. So right here-ish. All right. That's vector t. And then we have the vector u, 6, 11. That would be right here-ish. Not the best arrows. T and U. So the angle would be here. That would be theta. All right. So we're going to be using formula 2. Now, formula 2's derivation is really quite simple. I'm just equating both the geometric and Cartesian dot products together and then isolating for the ratio cosine theta. That's all. So let's begin. So cosine of theta, it's going to be t dot u. In this case, this top part is the Cartesian dot product, and on the bottom we have the magnitudes of each vector. Okay, so cosine of theta. So the vector u was 611. And the vector t was negative 7, 2. When you dot those, so I'm going to do negative 7 times 6 plus 2 times 11, and negative 20 on top. That's a negative number on top, which is indicative of what we see in the picture, because that represents an obtuse angle. And now the modulus of each of these guys, or the magnitude, is going to be negative 7 squared plus 2 squared. It's square root of 53 for t. And then for u, we get 6 squared plus 11 squared, which is square root of 157. So squared. So t, I'm just doing 7. And for u, I'm doing the same thing. All right. So then theta will be the cosine inverse of that. So cosine inverse of negative 20 divided by square root of 53 times square root of 157. Get 102.66 degrees. Nice. Moving on. We have question D. Let's do D. Just going to copy this. Okay. So what vector are we representing now? For D, we have the vector 2, 3. So 1, 2, then up 3 right here. 2, 3, that will be E, and then with the vector 9, negative 6, which is F. So 1, 2, let's add 2 more tally marks. 9, negative 6, so 1, 2, 3, 4, 5, 6. So right here. These are not the best diagrams, I will say. So this is the angle theta we're looking for. Theta. And the same deal. Cosine theta of E dot F. Magnitude of E, magnitude of F. Magnitude of E. So this vector was, scroll up again, 2, 3, and 9, negative 6. square root of 13. Magnitude of f was 9 squared plus negative 6 squared, square root of 117. Okay. The dot product now, again, component-wise multiplication, so 2 times 9 plus 3 times negative 6. That's actually 0. All right. Square root of 13 or square root of 117. So cosine inverse of 0, well, we know what that is. That's 90 degrees. So meaning I should actually change this. Oh. Should change this to look like so. It's perpendicular. Good. I guess we'll end off here for now, and we'll continue questions 4 and 5 for the next video.